Here we have a slightly more complex example. We have a loop. So we're iterating over all the items in this array and printing each item on the console. This is where the size of the input matters. If you have a single item in this array, we're going to have one print operation. If you have a million items, obviously, we're going to have a million print operations. So the cost of this algorithm grows linearly and in direct correlation to the size of the input. So we represent the runtime complexity of this method using the big O of n, where n represents the size of the input. So as n grows, the cost of this algorithm also grows linearly. Now, it doesn't matter what kind of loop we use to iterate over this array. Here we're using a traditional for loop. We could also use a for each loop. For example, for int number in numbers, we could simply print the number. We're still iterating over all the items in this array. We could also use a while loop or a do while loop. Now, what if we have a print statement before and after our loop? What do you think is the runtime complexity of this method? Well, you saw that this single operations running constant time. So here we have the big O of 1. Our loop runs in big O of n. And once again, we have the big O of 1. So the runtime complexity of this method is O of 1 plus n plus 1, which we can simplify to O of 2 plus n. However, when using the big O notation, we drop these constants because they don't really matter. Here's the reason. If our array has 1 million inputs, adding 2 extra operations doesn't really have a significant impact on the cost of our algorithm. The cost of our algorithm still increases linearly. So we can simplify this by dropping this constant. What matters is that the cost of this algorithm increases linearly and in direct proportion to the size of our input. If you have 5 items in the input, we're going to have 5 operations. If you have 1 million items, we're going to have 1 million operations. Now, what if we had 2 loops here? So let me delete these print statements and duplicate this loop. What do you think is the runtime complexity of this method? It's going to be big O of n plus n, or big O of 2n. This is another example where we drop the constant because all we need here is an approximation of the cost of this algorithm relative to its input size. So n or 2n still represents a linear growth. Now, what if this method had 2 parameters? An array of numbers and an array of names. So first we iterate over the array of numbers, and then we iterate over the array of names. Like this. What do you think is the runtime complexity here? Well, both these loops run in O of n. But here's the tricky part. What is n in this case? We're not dealing with one input. We have 2 inputs, numbers and names. So we need to distinguish between these 2 inputs. We could use n for the size of the first input and m for the size of the second input. So the runtime complexity of this method is going to be O of n plus m. And once again, we can simplify this to O of n because the runtime of this method increases linearly.